So this is the AP Calc mock AP exam number 3. So this number 1 here is meant to be 25 minutes long. I made this just an assortment of different types of related rate problems. So part A, person stands 40 feet from point Q and watches the balloon rise vertically from that point. The balloon is rising at a constant rate of 3 feet per second. What is the rate of change in radians per second of angle theta at the instant when the balloon is 30 feet above that point? So we know that this is going to be related rates because we have time all over the place. Everything is in relation to time. And we also know that we have to involve trig equation because we're trying to find angle theta. So we have angle theta, we have this y value variable. We also have this distance that is a constant value. So no need for a variable, but we have to involve this. So in order to hit all these three pieces of information, we're going to rely on a trig equation, and that trig equation is going to be tangent. So we say tangent of theta is equal to opposite over adjacent. So tangent of theta equals y over 40. Before we find the derivative, I'm just going to push that 1 over 40th out in front as a coefficient, so I don't have to think about trying to go through a messy quotient rule. So now let's find the derivative. Tangent theta, its derivative is secant squared theta and d theta dt. Since we're dealing with related rates, every variable is going to be affected by time, so every variable is going to produce its own d over dt. Now on the right side, 1 over 40 is a coefficient, so that's going to stay, and y becomes 1 dy dt. So this is the equation that we're going to have to plug in and solve for and use. So let's see some information here. We know the balloon is rising at a constant rate of 3 feet per second, so we know that's relating to this y vertical distance, but it's a rate of change, so we say dy dt is going to be a positive 3. What is the rate of change in radians per second? So we're looking for d theta dt when the balloon is 30 feet above that point. So at the moment when y is 30, we can use that information to help us gather pieces that we can plug in. So we have dy dt, we're looking for d theta dt, and what's missing is we need to figure out something to plug in for that secant of theta. So I'm going to rewrite that secant squared theta as secant theta quantity squared. And we don't know what theta is, but we can figure out the ratio of secant theta if we know each of the sides of this triangle. So at this moment in time, y is equal to 30. This horizontal distance is always 40. So if we use Pythagorean theorem, a squared plus b squared equals c squared, we can figure out that the hypotenuse must be 50 at this moment in time. And then if we do secant theta is just hypotenuse over adjacent. 50 over 40 reduced to be 5 over 4. We can place that for the secant of theta. So we say 5/4 squared times d theta dt is equal to 1 over 40th times 3 being the dy dt. And now we can just move things around to solve for d theta dt. So dividing both sides by 5/4 squared is the same thing as multiplying by the reciprocal of 4/5 squared. So 1 over 40 times 3 times 4/5 squared. This multiplies out to be 48 over 200, which reduces to be 6 over 25. And d theta dt, theta is always going to be measured in terms of radians, and the time unit is seconds, so radians per second. Part B, bikes A and B are traveling on perpendicular roads. At the same time, bike A and B are leaving. Bikes A and B are leaving the intersection at the same time. Bike A is leaving at a rate of 2 feet per second, and bike B is leaving at 3 feet per second. How fast is the distance in feet per second between them changing after 5 seconds? So I'm just going to label my sides with variables x, y, and z. dx dt represents the rate of change of bike A, which is 2 feet per second. dy dt is the rate of change of bike B, which is 3 feet per second. Okay. And we're trying to find the rate of change of this distance between A and B, which we can call z. I'm going to call z. So dz dt. So this is really just going to be a Pythagorean theorem problem. A squared plus b squared equals c squared. So in this case, x squared plus y squared equals z squared. Find the derivative with respect to time. So x squared becomes 2x dx dt. Then we have 2y dy dt, and z squared becomes 2z dc dt. We have dx dt, dy dt, and we're going to try here. We don't have x, y, and z provided for us explicitly. We have to find that on our own because the distance is going to be connected with this time unit, this 5 seconds later. So imagine these bikes are traveling at these rates, 2 feet per second, and after 5 seconds, what are the distances at these moments in time? And we can do that by multiplying the rate with how much time has passed. So for bike A, moving at 2 feet per second, 5 seconds later, it's going to be 10 feet away from that intersection. For bike B, moving at 3 feet per second, 5 seconds later, it's going to be at a distance 15 feet away from that intersection. And then using our x and y values, we can find out our hypotenuse. A squared plus b squared equals c squared. We solve for z, and we get 5 root 13. And once we have that z value and our x and y, we can now put in place of our differential equation, replace all the x, y's, and z's, replace dx dt and dy dt with 2 and 3. And that leaves us with the variable that we're trying to solve for, dc dt. So enter all this in our calculator, combine like terms, bring everything over, get dc dt by itself, and we get our approximation is 3.606 feet per second is how fast that length is changing between points A and B. All right, part C. A person 2 meters walks directly away from a street lamp that is 8 feet above the ground. If the person is walking at a constant rate and the person's shadow is lengthening at a rate of 4/9 meters per second, at what rate in meters per second is a person walking? So we'll let, this is going to be a similar triangle problem. We can set this up with the person being the height of the small triangle, and then the height of the large triangle is going to be the height of the lamp, of the street lamp. And I'm going to indicate this as x and this as y. So now we can set up proportions here. We can say we have a triangle within a triangle, so they're going to be related to one another using proportions. So I can say the height of the small triangle, 2, is to the height of the large triangle, 8, as the length of the base of the small triangle, which is y, is to the base of the large triangle, which is going to be x plus y. So make sure that you don't say x over x plus y. If you use a variable in my diagram, you're going to have to use y over x plus y. Okay, the x doesn't represent the full length of any base of triangle. Now, once we set up our proportions here, we can cross multiply. So 2 times quantity x plus y equals 8y. Distribute the 2 through, we get 2x plus 2y equals 8y. Combine like terms, 2x is equal to 6y. Now we can find the derivative. This is related rates. So 2x becomes 2 dx dt. 6y becomes 6 dy dt. Now, dy dt is the rate of change of the length of the shadow. Dx dt is the rate of change of the person walking. And then the two rates added together, dx dt plus dy dt, is the rate of change of the tip of the shadow, how fast the tip of the shadow is moving in relation to the ground. So dy dt is 4/9, that's given to us. And if I want to find dx dt, I can just take this and put it into my equation here. So 4/9 plugs in for dy dt, and we can just solve for dx dt. So we get 24 over 9 divided by 2, which is 24 over 9 times 1/2, reduces to be 4/3. So 4/3 is the rate of change that the person is walking. That's part A. Now part B is saying what is the rate at which the tip of the shadow is moving. So we simply just add the rates of the length of shadow with the rate of person walking, add those two rates together, and that's our answer. We get 4/3 plus 4/9 is equal to 16/9. That's the rate of change of the tip of the shadow in relation to the ground. All right, part D. Beach ball is deflating at a constant rate of 10 cubic centimeters per second when the volume of the ball is 256 pi over 3 cubic centimeters. What is the rate of change of the surface area? So the information that we can start off with is we know the surface area equation, we know the volume equation, we know this is going to be a related rates problem. We have time all over the place here, okay, per second, and we know we have to find the derivative. Let's see, gathering some information here. I know that this beach ball deflating at a rate of 10 cubic centimeters per second. I know cubic centimeters relates to volume, but per second means it's a rate, so that means dV dt is going to be 10, but I need to include the negative 10 because that volume is decreasing over time. So dV dt is negative 10. And we're trying to find the rate of change of the surface area, so we're trying to find ds dt. So here's my volume equation. I'm going to go ahead and find the derivative since we know everything's going to be related to derivative here with in relation to time. So v becomes dv dt. 4/3 pi is going to stay as a coefficient. We're going to find the derivative of r cubed, which is 3r squared, dr dt. Again, every variable is affected by time, but remember, pi is not a variable, so there's no need for d pi over dt. All right, that's just a number that's just going to stick with the derivative that hangs out in front. So let's see, we have dv dt that we can plug in, but we're trying to find dr dt so that we can use that to help us find ds dt, because ds dt is the derivative of the surface area, and we need to gather some more information. So we're going to use this 256 over 3 pi to help us out. We know that this is the volume at a moment in time, and if we know that's the volume, we can use that to help us solve for r. So we can say 4/3 pi r cubed is equal to 256 pi over 3. Pi's cancel out, multiply both sides by 3, then we divide both sides by 4, take the cube root of both sides, we get r equals 4. So if we have r equals 4, we can plug that in for our dv dt equation, and that can help us solve for dr dt. So I get 64 pi, divide that from both sides, I get 10 over 64, which is negative 5 over 32. The pi stays in the denominator. Careful about that. So this will give me the piece that I need to help me figure out something. It'll be a piece that I need to help us figure out ds dt. So let's go to our surface area equation, which is s equals 4 pi r squared. Let's find the derivative. S becomes ds dt. 4 pi r squared becomes 8 pi r dr dt. Or we can think of it as r squared becomes 2r dr dt, and the coefficient 4 pi just tags along. Multiply that out, we get ds dt equals 8 pi r dr dt. R we found from before, which was 4. Dr dt we found from that dv dt equation, which is negative 5 over 32 pi. And that leaves us with the only variable that we need to solve for, which is ds dt. Multiply this out, the pi's cancel out. 8 times 4 is 32. That cancels out with this 32. So we're just left with negative 5 square centimeters per second. So surface area is square centimeters, time unit is seconds, so negative 5 centimeters squared per second.